In this part of the workshop, I want to talk about machine learning with Julius Graph Engine. And well, for this, I will share a tutorial on which we are going to solve a basic machine learning workflow. So hopefully you're seeing my screen now. And well, here we are going to be solving the Titanic dataset, which is a well-known machine learning problem to predict the survival of the passengers of the Titanic. And for this, we'll be using the predefined rules and atoms available at the Julius data science package. And we will see how these rules cover operations such as data loading, visualization, and transformation. And then we are going to see the great capability of integrating with another language, since we are going to train the available Python models. Then we are going to use a higher order rule to measure the performance of multiple models and to tune the hyperparameters of said models. So hopefully that'll be really interesting. The first thing to do is configure the workspace, importing the libraries that we're going to use. And here's some Jupyter workspace configuration. And the first thing to do, we declare the config variable that is needed at the moment of the graph creation. With this parameter, you can set a project name in case that you need to run more than one graph. You can identify the graph associated to this project with this parameter. So let's begin and load the data. For this, we are creating our first node reference here through the rule DSL reference macro, and we are referring to the rule DS namespace. And we have two rules that support the loading of data. In this case, I have my data on a CSV file, but also we could load from a URL. And these parameters here are actually passed in the background to the csv.jl read function, which returns a data frame with the Titanic dataset. And this is the name of my file, and this is whether it has headers. And with this parameter here, we are setting a label for this node on the graph. So it will be easy to identify. So next, we want some information about our data in order to know what we need to do to work with it. And for that, in Julia and also in Python, in pandas, we have the describe function, which gives you statistics on the columns. So here, this rule, data summary, what it does is to take another node reference, and it will apply the describe function to the output of this rule. In this line here, we are creating an instance of a blank graph with our configuration. And in here, at the calc forward call, we are computing this graph. Here we indicate the name of the instance we created. And here we pass like this the final output of the graph, the final node, which is this one, the last we declare. And since every node must have information about the predecessors, about the dependencies, the graph can be computed recursively. Now, once the graph is computed, we can get data from any node that we want with the get data function. We specify the name of the graph and the name of the node that we want the output. And since every data must return a vector as an output, here with the 1 we indicate we want the output that's inside the first element of that vector, in this case, a data frame. And this is the result of applying the describe function to the Titanic dataset. We have the names of our columns and some statistics. And the first thing to do, we analyze this and see that we have missing values, and we need to fill those in order to work with this. Well, maybe Kevin here has too many missing values. This is most of our data set missing, so we are not trying to infer this variable. We are going to drop it. But we are going to fill embark and age columns. And for this, we have the fill missing rule under the DS namespace again. And this rule takes a node reference and a dictionary with the names of the columns we want to fill the missing values as keys. And here the values of this dictionary is the function that we want to apply, the method that we want to apply to this column. And this will operate over the whole column and fill the missing values with the result. We use the same rule as before, the data summary, to compute a summary of that. And we see that the missing values of embark and age are both gone. And well, now we can maybe analyze atypical values or things like that, but let's say that our data cleansing is done and proceed to feature engineering. And for feature engineering, well, we want to select the features for our models to train with. And for example, we may want to create new columns from the existing ones. So in this case, we have the fair column, which is a numerical one, and we want to normalize it, for example, subtracting the mean, dividing by the deviation, and now we have a new distribution for our fair column, center is 0 and with 1 as a deviation. Another thing we may want to do is reduce dimensionality. For example, in this case, this column is the amount of relatives a passenger has. This column is the total amount of relative a passenger has on the Titanic, since this represents the total amount of siblings and this the total amount of parents or children that are on board.
Sorry, Milena. Some people are asking to enlarge the screen, so if you can zoom in a little bit.
Oh, sorry, I wasn't really seeing. Maybe that's too much. That is it readable now?
Yeah, I think it's much better. Sorry
Thanks.
for that.
Okay, maybe can hide this as well and maybe enlarge a bit more. I don't know. Okay, thanks, Maro. So the next thing, after we declare this as a quotation, here we have two expressions with some information about the line of declaration of this code as well. And these are the new features that we are going to add. Then the features that we do not want to use, we need to declare inside of an array as expressions as well. These are the names of the columns that we are going to drop. And if we want to transform a data frame, we can use the call transform rule that allow us to pass a node reference with our data, then set a name for our operation, and then pass the new features and the drop features. And here we will have a node reference with our new data frame. We will compute a data summary again from that node reference, and we can see that now our new columns are here. Probably should have dropped these 3 as well to reduce dimensionality, and since now we are creating the new ones. But let's continue like this. This is an example. Here the mean is now 0, and this is the sum of these 2. So now we can compute our graph and see the whole workflow through the nodes information. And what's interesting here is that all the input and output of each node is cached in memory. So with the code of this cell, we can here pass the name of our graph, and we can visualize it through the Wave UI much better. And slow it. Ready to load. Yeah, of course. I also should check on the questions. Sorry, allow me to rerun all of the cells again. This is kind of laggy, probably through my internet connection. Let's access again to the tutorial. And I run all of the cells. Okay, there's the server running.
Yes, you can run all the cells again, Milena, just on the...
Yes, I think right now they are running. We are going to go through this again. Really sorry about that. Probably had my kernel going for too long and people is connecting, so you can always restart the kernel if you encounter an error like this. Another thing to mention is, for example, if you change a definition of a rule of a graph, it's a better practice to restart the kernel and run everything again. So now hopefully it will load. Great. Now we see our first node declaration that is here. And here we can see the atom that's applied to this node. In this case, it's alias. The alias atom allows us to refer the output of a different rule In this case, we are referring to this one that is performing the creation of an atom that outputs the data frame that we passed. Then we made a summary of that, then we fill the missing values, and you can always see the output here, then a summary, and then again feature engineering and a summary of that. So it's really easy to trace and debug what data we are going to use to train our models. Here we have everything is cached for every node, so it's not like you run these ones and then you don't really get explainability on why your model gave certain results. You can always debug really easily like this. And the next thing to do is to train our Python models. And for that, I want to present this PyTrain rule, this PyTrain atom that works as an interface with Python. Here you can pass a full name of a Python class to use. And here the options is a dictionary with the arguments to that Python class. And this step is creating the atom and a structure with these fields. And at the moment of the computation, we call the forward data function of an atom, and we pass the training data. And since the rule DSL supports multiple dispatch, here we can use polymorphism to define different behavior for different type or for variable. In this case, we have the classifier train rule that will call the desired PyTrain atom that we want to use, depending on the model that we want to train. So now we will see a higher order rule that will allow us to train all of these models at once and measure the performance on different metrics. And for that, first we need to declare a classifier spec object, classifier spec variable that will contain data about the models that we want to train, and also about the x's and the y's of our problem, and also some indexes used for validation and training, and the name of the target column. So first, we declare all of the models that we want to train like this as pairs, indicating the dictionary. This will be then the options variable here. So these are arguments for these Python models, all in scale-learn library, as you can see here. Also XGBoost. Then we are here declaring our target column. Here we want to select a portion of our data to use as validation and some other portion to use as training. So we can take a node reference, which is our clean data, and here select a fraction of the code that will be used for validation, and the rest will be used for training. So with all that information declared, we can create our classifier spec variable structure, passing the models and also our clean data. Here, notice that we are only passing the clean data, and the operation that we want to pass to it is passed separately on a tuple. Here is the name of the transformation we defined earlier and the new features. Also, we are passing the name of the target column and the validation indexes. So at this point, it's really easy to define different classifier spec objects, for example, to train different models with different transformations. So it's really easy to reproduce multiple experiments with this. Then here we define an array with the metrics that we'll be using and create a new node reference with the classifier metric high order rule. This rule will take our classifier spec object with all of the information of the models and our problem, and then we'll compute a dependent node for each one of these metrics here. So we can compute the graph with this node that we declare as a final output, the classifier metric. And we see here that this is all the time that it took to train all of the models and calculate the performance. So here all of the necessary classifier train rule has been called. And if you want to retrieve a result of the graph, you can create a node reference. For example, this node reference is a dependent node from this one, as this one calculated each one of these separate. So you can instantiate a concrete instance of a node and then search it on the graph with the get data function. And if we see the output of this, here we are just computing all of the output of this node. That if you check, this is a dictionary with both in-sample and out-sample metrics, and both point to a data frame with the metrics for each model. Here we are computing all of the metrics together in a new data frame. And well, as expected, we have much higher performance for the in-sample metric that is using the training data to predict. And this is how all of our models perform. Already they are trained, and we can see that how that happened through the graph. So here we have our data loaded. Here we made the missing values imputation, and we passed that clean source of data to our classifier spec structure. And here it just managed to do a split of the columns in the x's and the y's. Here you can see it saves the x's and the y's by separate. It applied the feature engineering to the x's and then memorized the non-numerical values to train the models. Then again, we use our clean data to select a random number of indexes for validation. And those indexes are used to split the data for training and validation. Here is where the model training is happening. And here we are computing the metrics. And what's really nice here is that, for example, you can define, as I mentioned, multiple transformations to train multiple models. And it's really easy to see what one model is being trained with. Because, for example, you can select show precedence. You just right-click and show precedence. And you see the full lineage of this node. So now it's really easy to trace all of the workflow and debug how your machine learning model is being trained. Then let's continue. Here we see that we can compute the total amount of nodes on our graph. There are 83 nodes. And now let's use the higher order rule hypertune to tune the hyperparameters of a desired model. Here we are creating node references to tune all of these models. We are passing again our classifier spec structure. And here we could pass, again, a dictionary with the arguments for these models in case we want to fix a hyperparameter or pass another argument. Here we are selecting the metric, and here the last argument is the hyperparameters that we want to tune. So here we will perform a grid search between these values, going 50 by 50, between 50 and 200 for the numbers of trees computed in this case. And like that, this rule will return the metric performance for each one of these combinations. Here we are just declaring another node reference that aliases. As we have seen, the alias atom just references the output of another node. Here we are referencing the output of all of these nodes. So if we compute our graph with this final output, recursively, all of this is going to be computed. And here we select, for example, we see that we created a new graph. And here, for example, we are calling to this dependent node, which is this one, the gradient boost model. So we are going to see the performance for that for all of the hyperparameters that we wanted to sweep. So here I'm not going to dive deep on which perform best, but we could say, for example, that we want a similar value between the in-sample and out-sample metrics, because a wide difference between these may mean that it's overfitting too much. For example, this one is widely different from this out-sample metrics. So for example, this one here may be better. I don't know. You should analyze this well. Then we can see our final graph on the web UI again. And this looks much simpler than before. We see that our classifier spec creation is the same, but here we should be training our model since we created a new graph with this output. So if we actually check at these nodes, we see we have an inner graph that we can inspect. And we see all of the training of the models is actually contained inside of that graph, inside of that node, sorry. So for that node, actually, this was the input and this was the output, and all of this was hidden on the background. So it's really easy to finally trace all of the input and output for each one of the nodes. Finally, as a conclusion, we can say that we are provided with rules that allow us to solve a machine learning basic problem. But of course, you can also define your own rules and your own atoms with your desired statistical operations or whatever you may need. And you can use the low-code macro syntax to add new rules and atoms. Also, it's really easy to debug our models, get some explainability of the results we have, since once you run the graph, all of the workflow data will be there, cached in memory for you to check. And also, it's really easy to reproduce multiple experiments with multiple transformations, different transformations, and those are really useful tools for this. Also, there's to remark that you do not need to throw away your work in another language, or you can use another language's really useful libraries, since we provide the capability of creating atoms that work as an interface, as mentioned, with another languages such as R, Java, C++. In this case, we see that we are provided with an atom that already allows us to train and model on scikit-learn on Python. And also, this scales really well. Probably one of the most important features is that you can connect your machine learning pipeline to a really high, a really large scale data analysis. For example, you may have a really complicated data gathering process, for example, or you may want to predict something that's happening live. And for that, you can stream data, really integrate your machine model training and prediction inside a full data pipeline. So that's a really useful tool to remark.